It's good afternoon. I am Lieutenant G. Somasundara Ori, behalf of Postgraduate and Research Department of Mathematics, DWARAKA Govardhan Das Vaishnava College. I welcome one and all to this webinar titled Some Applications of Graph Theory. So I welcome our college secretary, Shri Ashok Kumar Mundraji, our college principal, Captain Dr. A. Santosh Babu, convener and head, M. Venkatramanan, and all other professors, and today's resource person, Dr. N. Jain Karthik, and my colleagues and dear students. Thank you. Now we start this program with a prayer.
சீராரும் வதனமென திகழ்வரத கண்டமிழே எக்கணமும் அதிசிறந்த திராவிடன் நல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்து உலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் மிகுந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं ऋतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिः सतां दर्शनेस्तु भवत्तनूनां नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनामविभेदेन जगत्क्रीडति यो यतः ॐ शान्ति शान्ति शान्तिः.
I have a great privilege to introduce today's resource person, Dr. N. Jain Karthik, Associate Professor, Postgraduate and Research Department of DWARAKA Govardhan Das Vaishnava College, Arumbakam, Chennai. He is serving as a teacher for last 25 years, and he is expert in the latest research subject as a fuzzy sets and application of graph theory. He published 7 international peer-reviewed journals, and he delivered invited talks on symposium and national conferences, and also chaired a session for a paper presentation. He served as a subject expert in mathematics for qualification approval for assistant professors working in the affiliated colleges of University of Madras in 2019. And he is also served as a a NAC coordinator for DG Vaishnava College, and now he is presently serves as a NAC coordinator for our department, and he is giving a lot of inputs to the professionals, and he is sound in our technical sides. And now I invite our resource person, Dr. N. Jain Karthik, and hand over the session. So welcome, sir. So now
Good
session
afternoon,
is
sir.
yours. Yes.
I take this opportunity to thank everybody who has joined for this online webinar. I thank our Secretary, Sri Ashok Kumar Mundra, Principal, Dr. Santosh Babu, and our HOD for their support and guidance for conducting this event. So, the topic of the day is some applications of graph theory. So the graph theory history starts with the Königsberg Bridge problem. So initially, Königsberg was present day in Russia. It is there is a river, Pregal River, situated at that place. So the geographical layout was there are that area was connected with seven bridges. So people there wondered whether they will be able to uh, walk through the city, crossing each of the seven bridges only once. So the idea was they wanted to walk through all the bridges once and come to that starting point. So this was the problem that they were discussing. This is considered the starting point of graph theory. So here, regarding the solution of the problem, so it was observed that when we cross a bridge and cross back, then it means that at each point we have to have a degree 2. Here, Euler represented this uh, problem using dots and lines. So he represented the land area by vertices and he connected them, and he observed that whenever each vertex has a uh, line coming in, there should be a line that is going out. So he observed that this problem has no solution because it has odd number of uh, lines coming out from the vertices. So in 1735, Euler proved that Königsberg bridge problem has no solution. So this was considered the starting point of graph theory. So the idea of representing by vertices and edges. So this idea is very useful, and Leonhard Euler was also has made a lot of contributions to graph theory. He had, in fact, this type of walk is called Euler walk, and he also subsequently introduced the concept of planar graphs in graph theory. So we'll start with some basic definitions. So a graph usually consists of set of vertices. This set of vertices usually are also called nodes or points, and we have another set called the set of edges, and there is a mapping from set of edges to the ordered pairs of elements of vertices. So an example here, we have a graph with 4 vertices and we have 5 edges here. the edges are connecting 1 2 1 3 1 4 etc. uh, Actually, in optimization or operational research, this is called a network. So graph is a way of representing a network. So here, the pair of edges that are connected by an edge are called adjacent vertices. So here, in this graph, 1 2 1 4 1 3 are all adjacent. 3 4 2 4 etc. are also adjacent vertices, whereas 2 3 is not adjacent. Also, um, in real life, many situations can be represented by graphs. For example, say we can take four cities, and they have a connection or road between them. We can join them by a edge. So this graph may represent, say, some highway or some cities connected by roads. It can also be, graphs can also be used to represent social media. So we can consider people and join people as vertices, and join the vertices whenever they are a friend with the others, and so on, as in Facebook. Or we can also consider the Twitter example. When one person follows two, we can join them by an edge. And these are some ideas where, we can use the real life situation using graphs, and then we can easily apply the properties or optimization etc. That will be easier also. So we'll move on to the next idea, vertex coloring. So vertex coloring is assignment of color to each vertex in such a way that adjacent vertices have different colors. So whenever two vertices are joined by an edge, and that is known as an adjacent vertices. Whenever two vertices are joined by edge, and we will color them by different colors. So such a coloring which optimizes and minimizes the number of coloring that we would be interested in. So this idea is very simple, but it's very effective and useful. So there's an example here. Here we have a blue vertex that is adjacent to another vertex which we have colored with red. The other adjacent vertex we have used a different color here, and the last vertex is not adjacent, so we can, that is adjacent only to the red vertex. So that is in. So the same idea, instead of the vertex, we can extend that to edges also. In that case, that is called an edge coloring. An edge coloring of a graph is coloring of edges such that adjacent vertices different receive different colors. So in this age, the adjacent ones will get a different colors. So instead of the vertices, we will be coloring with the edges. So to restate the idea in a different form, so we have a graph with four vertices. So a graph, we'll say, will be colored if the color has been assigned to the vertices such that adjacent vertices have different colors. So in this graph, we have four vertices. We'll be started coloring the vertices. Actually, the idea of coloring is assigning a label here for simplification of that idea, abstract idea. We'll be using colors. Actually, it is labeling of the vertices. In fact, the idea of coloring a graph initially started from the way the map was colored. We have already have a conjecture saying that a map can be colored with four colors. A planar representation of a map can be colored with four colors. That is a famous conjecture. So from that idea, the graph coloring has originated. So here we'll be coloring the vertices. We'll start with the vertex 1 here. So vertex 1, we can start with any random color. So we'll start with color blue here. So its adjacent vertices are 2 and 3. Since 2 and 3 are adjacent, we cannot give blue to 2. We can give some other color to 2. So here, no, I'll consider giving color red to 2. Now we have two edges from 2. So one of them is 3, one of them is 4. Now for 3 we have a problem because it is adjacent already with 1 and also with 2. So we cannot give blue or red here. So we have to go with another color. So we'll take up another color. So that now we are left out with the last vertex. This vertex is adjacent with 2. Now we cannot give red color. We can give any of the color, either blue or yellow. So we'll go with blue. So we are able to color this graph with 3 colors. So when we are able to color a graph with 3 colors, this is called the chromatic number of graph. Chromatic number means it is the minimum number of color. That is the smallest number of colors with which we can give the graph a proper coloring. So in this example, the chromatic number is 3. As an applications, we'll be taking up with scheduling problems. So scheduling problems are problems where we uh, give a set of jobs. So we'll be uh, giving the jobs some time slot or the way in which it will be performed. So sometimes we have some constraints saying that some jobs have a conflict. So that is because we cannot assign the jobs continuously, or that may be because of they rely on the same resource or there is a conflict. So sometimes we will not be able to schedule it at the same time. So what we do here is we assign the graph a vertex for every job, and we join by the edge for every pair of conflicting jobs. Then we color that using vertex coloring or edge coloring, or depending on the problem. Then the chromatic number of the colored graph will give you the optimal time to complete all the jobs without conflict. So the scheduling problems can be deciding which staff should work on which shift, or it can be scheduling of examination. So scheduling of examination. So we know that the students will have a different examination that should be scheduled with the minimum number of slots. So the conflict there will be the students should not have subjects they are appearing on the same time, and we can use the same problem like scheduling of rooms for meeting. So we may have few auditoriums, and we may require them. We will have some number of meetings, so we may require the minimum number of in the minimum number of auditoriums we have to schedule the maximum number of meetings. How it can be done? And another area will be we can schedule matches or tournaments in a sports league. So those kind of examples also can be done. So actually, the situation, there are a lot of situation where scheduling problems has been can be applied. Usually, the scheduling problems you can use optimization techniques like OR, graph theory, etc., and you can even combine them and use it. So, as an example, we'll take up this problem. Here, we need to assign lectures. So, we'll assume that BSc Maths, BSc Statistics, BSc Computer Science, etc., have these open electives, and our aim is to schedule them so that all the students will be able to attend the lectures, but we have some conflicts. For example, the conflicts are no graph theory. The students who have taken graph theory also have taken algorithms and programming in Python. So that is our constraint. So graph theory cannot be scheduled with either algorithms or programming in Python. So fuzzy sets, for example, that is the second elective, that cannot be scheduled with graph theory or programming in Python or numerical analysis. So we have a lot of constraints here. So our idea is to schedule this 9 electives without the conflict and in minimum number of time slots or rooms also, whichever is the constraint, we may apply like that. So here this problem can be represented in a graph. So what we do here is the conflicts. So there are 9 subjects here. So the 9 subjects can be represented by 9 vertices here, and we join the vertices by edge when there is a conflict. Here, so graph theory is in conflict with 2, 3, and 4. So V2, V3, V4. So we join V1 with V2, V3, and V4. Similarly, the second directive is in conflict with 1, 4, and 5. So we join V2 with V4, V5. And similarly, we complete the diagram here and we get this graph. So this graph is, so we have represented the given problem as a graph. As a solution, so what we do here is we'll find the chromatic number. Chromatic number is the minimum number of colors required to color this graph, and the problem what we have in hand is the adjacent vertex will not receive the same color. That is the condition, and we have to find the minimum number of colors. So the minimum number of colors gives the chromatic number. So here we start with blue. We have vertex 2 which is adjacent to that. So we can give a color here. Since it is adjacent to one, we have to go for another color. Now we take up V3. V3 is adjacent with V1. So it is not adjacent with V2. So we can give the same color here. Now if we take V4, V4 is adjacent with V1, V2, also V3. So we cannot give either blue or yellow. So we have to go for a new color. So we'll take up another color here. Now V5 we take, that is in adjacent with V2, also V4. So we can give the color blue itself, since it is not adjacent with V1. Now if you take V6, so V6 is adjacent with V3, also V4. So you can give the same blue color. Now V7 if you start with, V7 is adjacent with V3, V4, V6. So we cannot give blue, green or yellow also. So we have to give another color. So we have to introduce another color, V7. So now for V8, it is adjacent with V5 alone. So when it is adjacent with V5 alone, we can give the same color as green. Now V9 is adjacent with V4 or V5. So we can give the color red. So we are able to color this graph with three colors, four colors. So the time slot will be, so blue meetings we can schedule from say 9 to 10. Then yellow meetings we can schedule from 10 to 11. So the red meetings we can schedule from 11 to 12, and 12 to 1 we can schedule the other meeting. So rather this time doesn't matter. We have four slots here. So we are able to color this graph in four colors. So the chromatic number is 4. So we have 4 time slots. And we see that uh, blue we have 3 vertices here. So we need 3 rooms. And for the other meetings, we require just 2 rooms. So in this way, we can schedule the electives in say 3 days. So similar example we'll take up. This problem is called frequency assignment problem. So so generally we'll take the radio transmitter in a region. They cannot in broadcast in very nearby frequencies. So when they do that, there will be some operational problem. So it needs to be assigned. So what they do usually is, we can denote the stations that are transmitting, the radio stations we have, that they have radio transmitters. So those we can select them as vertices, and we join them by edge if they are in a certain distance. So if they are in a certain distance, then if we are able to apply vertex coloring, and that coloring will give you the frequency that will not interfere. In this way, we can solve the frequency assignment problem. The frequency assignment problem, we can use that for our mobile connection also. Radio, it also works similar to our radio signals. Mobile phone, we have our GSM network, so that works by searching for cells in the immediate vicinity. So GSM network will operate on usually on four different frequency ranges. Usually that is because we have four colors for planar graph. That is the number of colors we usually have. So vertex coloring algorithm we can assign here, and we can solve this frequency assignment problem similar to our scheduling problem. So the idea is same, but it can be implemented in different scenarios. In chemistry, there are different chemicals that usually react violently when they are in contact with each other. So what we have to do is, so they can be corrosive, oxidizer, flammable liquid. They are highly reactive. So some of them cannot be stored together. So we have to. So suppose a manufacturer manufactures all type of chemicals. He needs to store them. So how we can store it in so efficient minimum number of storage way. In that case, what we can do here, we can select the chemicals as vertices and join them by edges if they are reactive or they should not be in contact. In that case, if they should not be in contact, we join them by edge. So then we start coloring it. The chromatic number gives the minimum number of areas where the chemical can be stored. So whenever we want to store it, this chromatic number will give you the smallest number of storage area required to store the chemicals. So in this way, we can efficiently store the chemicals. The similar example can be adopted for storing of or in a zoo or anything. If you want to, we want to have animals in their enclosures. So how many enclosures is required to optimize it, or it can be a scenario in a zoo or a pet store, or here we have a problem where some animals may attack each other. They cannot be put together. So in such cases, we select the animals as animal species as vertices, and we can join them by edge when they don't go well or attack each other. They should not be. They cannot be put together. In that case, we can join them by edge, and similarly, we can apply vertex coloring. The chromatic number will give the efficient way of storing them in the separate enclosures. So this is the same idea we can apply for zoos or pet shows, or even fishes or something we have in our pet tanks. So there also we have the problem of some fishes may attack the other fishes. So same idea can be applied in our aquarium also. So in computer science, we have that for the program, the system will allocate registers. It depends on the storage of the program. In our example, suppose A is the input, suppose B is equal to a function in terms of A, and C is a function that depends on B and A. Now, if you are storing it in variables, so whenever we have to give a coloring. So A and B, so B is in terms of A, so A can be adjacent to B. So C is adjacent to both A and B. So when we make the coloring, So they get different colors. So like this, we can keep storing the variables. Once the variable loses its value, we can assign the same storage location. For example, in our case, so the A storage location, once we have calculated up to C, A location is not required anymore. In that case, the same location can be used to store the next variable D. So D is again assigned in terms of B and C. So the values of B and C is stored in D, and like that, whenever the value of D is not required, we need another variable. We can use the same location for E also. So like this, by using vertex coloring and also chromatic number, we can allocate the minimum number of registers. So the idea is, once the register is not required, we can use that to store another variable. So by using this, we can reduce the number of storage equation, so thereby efficiently using the register. So this is another interesting problem. We have a website called Wedding Seater Plan. So what they do usually is, this is also a scheduling type of scheduling problem. So maybe we have a wedding or official meeting or whatever you have. We have so we can plan the seating. So we'll consider the example of wedding itself. So in the wedding, we have a different set of people coming. So maybe from the groom side, maybe from the bride side, maybe from the parents side, parents of bride or parents of groom. It can be their relatives, it can be their friends, it can be their colleagues, etc. We would like to um, make their banquet seating such that the colleagues sit together, or friends, they sit together, or even relatives sitting together. So in that case, how we can make an assignment? So this wedding seater plan, that's a website actually. So if you give them the input of which people will be coming and what is the restriction, and they will be able to plan out and give you the seating layout. So we will take up a small example how we can implement this. So for example, we have our seven types of guests, and each guest we have the companions also. It can be two, it can be three, it can be four. So for our example, we'll consider up to four companion. So here we have a restriction also. So maybe A and C will not sit together, and B and D will not sit together. So A and C will not sit together means C and A also will not be assigned the same place. And B and D or D and B, it's the same thing. So it's a symmetric relation. So C and A will not sit together. So we have a restriction like this. So we have to plan their uh, seating arrangement. So based on this condition. So here, no, this is the conflict. So we have from vertices from A to G. We'll draw the vertices here and connect them by vertex with the conflict. So here the conflict is A and C will not sit together. So we'll join them by a vertex, and say B and D will not sit together. So we join B and D also. Similarly, C will not sit with A. C will not sit with E or F also. So we join them. D will not sit with B. That has been taken care. So we'll complete the graph. Now we'll try to color the graph. So we'll start with a color blue here. Now C is adjacent. So she should we can color C with a different color. Now we have B and D, which are no way. B is adjacent to D alone. So we can repeat the same color here. Now, if you go to the next C, E and F are adjacent to C. Also, E will can get any color, because again we have F here. So C and E, they are adjacent to F. So we can give a new color here. And G is a separate vertex. So that is a separate guest. So that it can be accommodated. So now we can see that the chromatic number of the graph is 3. So 3 tables will be required. The first one will have more number of people there, whereas it depends on the chair we can see, but 3 tables will be required. So efficiently we can schedule tables like this, and no, you can. This is actually a website which offers solution to people having programs like this. So we'll move on to the next example. We have seen no matches. So, for example, we have our tournaments. We have a football World Cup or a cricket World Cup, where number of uh, teams we have, and we have to schedule the matches. And most probably, we would like to schedule them in a round robin league. So this is one type of uh, popular method, where each team will play against all the other teams, and based on their ranking or performance, they will be eliminated or selected for further rounds. So usually we'll consider the case of round robin tournament involving n teams. So each team is required to play. Um, so we'll take it as m times. So that is m rounds are there. So most popular rounds are m is equal to 1 will be single round. That is, each of them play against. So each team will play. So there are n teams. Each team will play against the remaining n minus 1 teams, and that is one type of thing. And sometimes the tournaments like IPL we have, there may be, two round robins. So each team will have a home team, home ground, and they'll have one match in the home ground and the other team's home ground. So that is two types of round robin. We can consider both also. So as an example, we'll take up a smaller number of teams. So we'll be using edge coloring here. So 4 teams will take up. Some teams, 4 teams from Asia will take up. So India, Sri Lanka, Pakistan, and Bangladesh. Now they have to, 4 teams are there. So how many matches will be there, and how we can schedule them? So 4 teams play each other. So we can count the number of matches here. The first team is India. Second team is Sri Lanka, Pakistan, and Bangladesh. So we'll take up India first. India will have to play with Sri Lanka, Pakistan, Bangladesh. So we'll be completing 3 matches there. Then the next match will be Sri Lanka and Pakistan, Sri Lanka and Bangladesh. So thereby we have covered all the matches for India and Sri Lanka. Now we are left out with only Pakistan and Bangladesh. They will play a match. So totally, so there will be 3 plus 2 plus 1. So 6 matches will be there. So how do we schedule this 6 matches? So to schedule the 6 matches, uh, we'll be using edge coloring. So here we start with the first match 1 and 2. So we'll give a color here. So the first match, we have started with the first match. Now for the second match that involves 1, we should not give color red here. So we cannot give color red for the uh, line from 1. Similarly, we cannot give color red to the line coming from 2. So we'll take up, so we have already colored 1 to 3 by blue, 1 to 2 by red, 2 to 3 by blue. Now, if you take the next match, we'll take up 1 to 4. 1 to 4 can be given black color. Now, we are left with 2 to 4 now. So, again, 2 to 4, we cannot give. For 2 to 4, we cannot give either red or black. We have to give blue. Now we have left out with 3 to 4. 3 to 4, again 3 is adjacent with black and also blue. So we have to color with red. So here we have colored that with 3 colors. So we can cover the matches in 3 days. So the blue matches can be scheduled in same day. So 1, 3, 2, 4. So 1, 3 is India versus Pakistan, and 2-4 will be Sri Lanka versus Bangladesh. And second day we can cover 1-2. So 1-2 will be India versus Sri Lanka. 3-4 will be Pakistan versus Bangladesh. That can be completed in the second day. On the third day we can have 2-3. That is Sri Lanka versus Pakistan, and as well we can cover India versus Bangladesh. So, so normally we have 6 different matches. Instead of scheduling them on 6 days, we can schedule them in the weekends, and depending on the stadium availability or anything, so that we can maximize on the audience, and audience can also will be able to see the matches. So we can cover them in 3 days, and that will also possibly in the weekends or whichever is convenient, the event can be scheduled. So this is, for example, scheduling of. At present, we have 8 teams in the IPL. So we have a edge coloring here. So each team will meet the other 7 teams. So you can easily schedule the matches. So this example, looks a bit difficult, but scheduling them by coloring makes it easier. Now we have a computer program which can be run. The number of teams is more. For example, the basketball league like NBA has 30 teams, and many of the football leagues are no, they have a large number of teams. Scheduling also is difficult there. So we can rely on this one, and depending on, we can give the constraints also, like how many teams, how many stadiums is available, and make preference for end of the week, maximize on the stadiums, and uh, convenience of the people. It can be scheduled on weekends or whatever slot is available. So that will help the plan. So this kind of graph, um, we have seen here, is a complete graph. So here I can tell the graph, a graph which a team plays with all the other teams, round robin team. So that is generalized. We can, that idea can be generalized, and that is nothing but a complete graph. A complete graph with n vertices. So in graph theory, this is denoted by kn. So each vertex is connected to the remaining vertex. So each vertex is connected to the remaining vertex. So we can see here K1 graph has only one vertex. K2 will have two vertices that joined by only one edge. So K3 graph, if you take, so K3 graph is like 3 teams playing against each other. So A, B, B, C, C, A. So 3 matches will be there. K4 example, we have seen 4 teams playing against each other. So here each team will play 3 matches, and the idea is extended. K5, we have 5 vertices. each vertex is connected to remaining 4 vertices. You can extend the idea. We have K6, K7, etc. So to restate the idea, so a complete graph can be viewed as a model of round robin tournament, and we can say each vertex represents one team, and you can join them by edge. So ij will represent the game between them. Also, you can consider this as a party where a person, each person shakes hand with the other. So how many handshakes will be there? So that is the handshaking lemma. That is a famous lemma in graph theory. So we'll take up the generalization of this example. We will be able to generalize. So a complete graph, for example, can be viewed as the round robin model. So each team will play against. So suppose for the generalization, there are n teams. Each team will play against n minus 1 team. Here, for our example, 4 teams were there. They were scheduled against 3 of them. So each team will play against n minus 1 teams. So the number of matches will be n into n minus 1 by 2. That is because each team, there are n teams. Each team will be playing against n minus 1 opponents. So the total number of matches will be n into n minus 1. But here, we are counting the match as 2 because we are counting the match for India once and for Pakistan once, like that. So when we divide by 2, we'll give the total number of matches. In this case, for 4 vertices, each vertex is connected to 3. So 4 into 3, 12 vertices will be there. But we have counted the match twice. So that should be divided by 2. That makes 6 matches. So the same idea can be extended. If there are 2 rounds, then that will be n into n minus 1. So we'll take up next example, an interval graph. So this kind of graph is uh, formed with set of intervals on the real line. So whenever the edge joins between them intersect, it will give you the interval. For example, the graph we have, we have the intervals there. So A is the blue interval. Down there, the graph is given. So it has some events like B and C overlapping with that. Then we have D, E. So C and D are overlapping event. E and F are not overlapping, whereas G and F are overlapping. So what we can do, when the interval graph is given, we can draw our regular graph from that. We join them by edge when they are overlapping. For example, A vertex is connected with B and C because they have overlapping lines. A and E are not connected. A and E and F are not connected, and so on. So this interval graphs have a good application in scheduling also. So this example we will see. So we have no famous apps which schedule taxis, or even scheduling problems like flight scheduling, for example. So suppose in case we don't have a straight flight, we have to take up a flight from A to city B, from city B to city C, like that. In that case, we cannot take a overlapping flight. So suppose we'll come to this example, taxi scheduling. Suppose a taxi company has 10 different bookings. Depends on the time. Say booking 1 is booking 2, like that. And suppose we need to schedule the minimum number of taxis for this. So what we do here, we select the overlapping taxis. So 1, 2, 3 are overlapping. 1 and 4 are not overlapping. So 1 is connected to 2 and 3, right? 4 is also overlapping. So we'll connect 1 to 4 also. 5 is not overlapping with 1. It starts after 1. So 5 will not be adjacent to 1. 5 and 6 are overlapping. So we'll connect 5 and 6, and even 7 are overlapping. So 5, 6, 7 are connected by edges. Then 8 starts after 7. So 8 and 7 are not adjacent. Then 8 and 9 are adjacent, overlapping. So we'll join them by vertex. Then 9 and 10, for example, are overlapping. So we join them by vertex. Now the next step will be, we'll be coloring this graph. So adjacent, the vertices will not receive the same color. So we can color 2 and 3 because they are adjacent to 1 by different color. Then go on to 5 again. 5 again can assign the first taxi itself. Again 6 is adjacent, 7 is adjacent. So 5, 6, 7 we have done. So far we require 3 taxis. Now we can start with the red taxi itself. Then again this is adjacent. So eventually we will be scheduling with the trip. The red taxis or the red vertices 1, 5. Those trip can be taken by red taxi. 2, 6, 2, 4, 6, and 9 can be taken by the second taxi, and blue taxis will be that 3 and 7. So the journey 3, trip 3 and trip 7, you can send the blue taxi. So in this way, we can easily schedule. So next example, what we'll take, we consider the case of a weighted graph. So normally, when the edges are adjacent and we have drawn that. Sometimes in natural scenario, we represent, for example, the road example you can take. So city A to city B, if it is at a distance, we can give that weight. It can represent cost or whatever may be, depending on the context. So this kind of problems are traveling salesman problem. Those things also can be solved using this technique. So we have seen Google Map. So Google Map, every app uses Google Map using GPS. GPS is the global positioning system. Using that, it is able to collect the real time uh, position of the thing, and we can it will deliver. It will give you the real time situation. What is the route you can take to from place A to place B? So how it can do? So the advantage of Google Map is it saves a lot of money because we can plan our trip in real time, and depending on the time, it will give you the expected time also. And in case the travel time is more, the route is very filled with traffic or anything, it will suggest you the alternate path or route wherein you can take up and travel in the time. So this Google Map uh, uses A star algorithm. So that is a graph algorithm that is for weighted graph to find the shortest path between two vertices. Now the advantage of using this algorithm is it takes into parameter the time, distance, and efficiently how we can apply. So here, for example, I'll take up a simple example. Here we have vertex A to vertex J. So we want to travel from start to A to J, and the measurements of the routes are known here. So which is the best path, or the so we'll have some weights also that will give you the idea. So we can start with A. So A has two adjacent vertices, B and F. So we considering the weight here. So the initial weight will be from A to B. The traveling weight is 6, and for B the weight is 8. So totally it is 14. For F path it will be 3 plus 6, that is 9. So we will take the path which has the minimum weight. So the path will start with A to F. Now what we do is A to F is fixed. From F we have to find the path. Now we have two vertices here, G and H. Again, we do the same thing from A to G. What is the minimum uh, weight we have to consider? So for G, it will be 3 plus 1 plus 5, 9. So we do keep doing this, and we can find from A to F to G to I. So we'll choose the minimum path. So this kind of algorithm works in Google Map, and it is able to give us the shortest path in the real time. So our solution will be A to F, F to G, G to I, and I to J. In case you have a alternate thing, that also can be suggested. So with this, we have conclude the end of the session. Graph theory is very important, and it is very useful in modern life. What we have seen from the thing is, a solution to single graph theory problem can have many different real world applications, and graph coloring is one of the important research field in graph theory. It is very simple to understand and apply, and not only that, the research topics in graph theory can be built into a model also, and we can have many apps working, and it is very uh, say not only as a research topic, it is implementable model also. So with this, I conclude my talk. If there is any question, I can take up.
So thank you, sir. Sir, actually, in a comment box, there is no question, sir.
Okay, thank you then.
Okay.
Thank you for the
Okay.
opportunity. Thank you.
So thank you, sir. This is a formal vote of thanks. As I'm very happy to thank our college secretary, Shri Ashok Kumar Mundraji, and our beloved principal, Dr. S. Santosh Babu, convener and head, R. Venkat Ramanan, and today's resource person, Dr. N. Jayant Karthik, for his wonderful speech. And today, sir, you were enlightened. It's a very great thing. Then here today's we see the application of the graph theory in exam seatings, then the elective subject selection, then chemical storage, and zoo, the animal separation, in particularly marriage, the seating arrangements, then frequency allocation, then very interest topic. We've seen that one. There's a round robin sports league. What the IPL matches, how they are scheduling. Then each team is playing with the other team, the n-1 teams. Then the number of matches will be n into n-1 divided by 2. If two matches they are playing, then it is by n into n-1 number of matches. Then the new topic, it is called the interval graph. That is the taxi scheduling using a vertex coloring in a interval graph. So we see that what is red, yellow, and blue taxis, how they are allocating the companies. Then the weighted graph. Then finally, Google Map, the intelligent transportation system, and the shortest path using algorithm. Then the final touch we given how the graph, it is a real-time problem, how it is using. Then it is also very easy. So we learn graph coloring and graph labeling, then spectral graph theory, fuzzy graphs, and network and flows. So this is as enlightened and given a very good introduction and create interested towards the students and staffs. So very thankful, sir. And once again, I thank you one and all. And tomorrow, so we have a webinar that is introduction to the fuzzy sets and their applications by Dr. B. Abhirami, Assistant Professor, Postgraduate and Research Department of DWARAKA Das Govardhan Das Vaishnava College, Arumbakam, Chennai. So we meet tomorrow, 2 o'clock. Thank you. Your feedback link is in chat box. As a kindly give your feedback. Thank you. Sir, feedback link in your chat box. As a kindly give the feedback. Thank you.